24.53 gigabytes per second. That is the peak throughput of the new GigaToken library. To put that metric in perspective, when encoding the GPT-2 vocabulary, GigaToken processes the exact same dataset 989 times faster than the HuggingFace baseline. For engineers accustomed to Python bottlenecks, the immediate assumption is that this throughput results from porting old code to a faster language. However, HuggingFace and TikToken are already written in multi-threaded Rust. Achieving a 1,000-fold speedup using the same programming language indicates a complete architectural overhaul rather than a simple tooling upgrade. Historically, tokenization is treated as a fixed-cost tax in every language model training pipeline, an invisible but mandatory expense. GigaToken optimizes this step to the point of near non-existence. Eliminating this specific computational tax alters the timeline and cost structure of preparing the massive datasets required for AI training. The first required step in this pipeline is pre-tokenization, breaking raw text into isolated chunks before assigning integer IDs. Traditional NLP pipelines rely on general-purpose regex engines to execute this chunking process. The flaw with regex lies in sequential evaluation. Processing text character by character creates massive computational friction when deployed at scale. To solve this, GigaToken implements SIMD execution, single instruction, multiple data. SIMD allows modern processors to bypass sequential reading and handle multiple data blocks simultaneously. GigaToken strips out regex entirely, replacing it with hand-optimized SIMD instructions tailored for specific CPU instruction sets, like AVX512. Relying on SIMD eliminates branching logic, which is the primary cause of CPU pipeline stalling in traditional tokenizers. Tailoring the parsing logic to the physical layout of the CPU shifts tokenization from a software abstraction to pure hardware exploitation. Once the text is chunked, we hit the final encoding step, where text chunks are mapped to their integer IDs. To save compute cycles, tokenizers use a pre-token cache. If a word has been seen before, the system retrieves the encoded ID from memory rather than recalculating it. This chart illustrates Zipf's law. Human language consists of a few highly repetitive words, the sharp spike on the left, and a massive, endless tail of rare words. Standard caching fails because rare words infinitely inflate the cache size, destroying memory efficiency. GigaToken optimizes its cache hierarchy to target the highly repetitive head of the language distribution. This targeted approach prevents the CPU from wasting memory and processing time on rare string evaluations. Exploiting the statistical predictability of human language turns the most computationally expensive step into a near-instant memory retrieval. Moving to the broader execution environment, while machine learning pipelines are orchestrated in Python, the heavy lifting occurs in Rust. These zones meet at the ABI3 boundary, the interface layer where data structures must be translated between Python and Rust. Passing millions of individual strings across this specific boundary creates invisible pipeline friction that throttles standard tokenizers. The GigaToken API bypasses Python for file ingestion, reading massive text files direct from storage into Rust memory. This speed exposes the limitations of traditional multithreading, where concurrent threads must constantly communicate to avoid overwriting each other. GigaToken solves this by pre-splitting massive files, like the 11.9 gigabyte open web text dataset, at safe boundaries like the end of text marker. This architectural choice allows individual CPU threads to process 100 megabyte chunks in absolute isolation. Zero communication threading ensures that simply adding more CPU cores yields linear, unbroken performance gains. Avoiding Python data structures and thread locking removes the software completely from the critical path. Performance is no longer dictated by software coordination. It is limited strictly by the raw speed of the silicon. Real-world benchmark data proves that these micro-optimizations scale across radically different environments. On server-grade hardware, the AMD EPYC 9565 exploits zero communication threading across 144 cores to hit the 24.53 gigabytes per second peak. This architecture remains effective on consumer hardware. On a 16-core Apple M4 Max using Neon instructions, GigaToken remains 1,200 times faster than the HuggingFace baseline. Modern standards like Llama 3, Qwen, and DeepSeek all benefit from this increased throughput. While older sentence piece-based tokenizers like Llama are currently less optimized, they still vastly outperform incumbent libraries. Cache hit rates and SIMD lane widths dynamically adapt to the available hardware on the host machine. GigaToken's low-level architecture makes massive-scale tokenization hardware-agnostic, enabling hyper-efficient data preparation on both enterprise server racks and standard laptops. To understand the impact, we must look at the physical scale of foundational training datasets. Take Common Crawl, a 130 trillion token repository representing the entirety of the written internet. Preparing this corpus historically required massive distributed server clusters running for days or weeks. Applying the GigaToken EPYC benchmark to the Common Crawl corpus reduces that timeline to exactly 6.5 hours on a single machine. Processing the entirety of the human internet is no longer a distributed engineering nightmare, it is a localized afternoon task. Because tokenization now runs at the physical limit of memory bandwidth, the bottleneck in AI development has moved. Optimizing a core algorithm by a factor of 1,000 collapses cloud compute expenses and forces the entire artificial intelligence industry to reevaluate what is physically possible on a single machine.